بسم الله الرحمن الرحيم. Assalamu alaikum wa rahmatullahi wa barakatuh. Dear friends and colleagues, distinguished guests, ladies and gentlemen, good evening. Hello and welcome everyone. And thank you for joining us. This is the fourth day of the virtual course of Deep Dive into Clinical Research, Part 1. Hello everyone and welcome back to today's session. Through research, our curiosity and the questions grow. Through research, we change, prospered, and improve. Through research, we found answers, solutions, and cures. Just a little housekeeping before we get started. If you have any question during the presentation, please type them in the Q&A box. At the end of the lecture, the speaker will answer your questions if the time allows. If there is no time, I will reach you later with answers through WhatsApp or email. And the recorded version of this webinar will be available for 30 days. We will send you a link after we finish Part 1, and your questions and comments are welcomed throughout this period. Thank you again for your joining us in this journey. We wish you all the best in the course. You are collecting data, but they are not clean. What's next? To know, let's deep dive with Dr. Anas Al-Hammam into clinical data and data management. Please join me in welcoming our eminent speaker, Dr. Anas Al-Hammam. Welcome, Dr. Anas.
Assalamu alaikum, يعطيك العافية دكتورة دنيا. Thank you very much for the very generous introduction. Welcome everyone. Today I have the distinct pleasure of talking to you about data cleaning. It's part of the analysis chapter of this research event. I'm sure that what I'm about to tell you is going to be an introduction to the next speaker, Dr. Imad Khoja, and the speaker after him that will tell you about the analysis and the different ways of going about cutting up your data. But before you do that, you need to clean things up. This is something that we do instinctively. We don't really think about it that much, but I need you to have a look at why we do this, how we do this, because if you're not aware of certain aspects, you will actually be introducing some bias and some errors into your data set, which you might not be aware of. And this can actually translate to a change in what you are observing, not because it is what you're observing, it's probably because what you did to the data set. So first of all, I have no disclosures, no conflicts of interest to speak of. So what is data cleaning? A lot of you might know or may not know or have heard the term data mining, which is not data cleaning. And I will point out the difference in a moment. Data cleaning is very simply a process by which the collected data or the raw data or the dirty data, as we call it, it's the data that we get from the study, is processed to remove the corrupt parts of the data, the incorrect data, the duplicated entries, things that can actually make your results somewhat inaccurate. Same thing, some people call it data scrubbing, data cleansing. It's kind of the same. Basically, what you need to do is get rid of the stuff that you don't need. The idea when you go into a research project, since you're already putting in the effort, you're spending the money, you're getting people to help you to do the research project, it makes sense that you collect as much data as you can. And then the stuff that you don't need, you may just remove from your presentation or your manuscript. In fact, a number of projects can actually collect data for 2 or 3 different study presentations or different articles. They, of course, use the same population, they use the same framework, and since you're already doing the job, you might as well get as much as you can, and then if you don't need it, you can just remove it. It's a lot better than requesting data that you want and then you find it to be missing. So what is the difference between data cleaning and data transformation? Data cleaning has to do with improving the quality of the data, improving the content, removing the errors, removing the stuff that you don't need that does not pertain to your particular question or to your project. And basically, it's just going to hinder you, especially if you're using a lot of data from multiple sources. This can be a problem. Okay, data transformation is making the data easier for analysis. So you're kind of putting it in the language of the program that you're using, whether you're using Excel, whether you're using Access, whether you're using SPSS. It's basically what the analyst changes the data to, so that it's much easier for them to do calculations on, it's much easier for them to enter. So things like if, for example, you are taking a survey and you want to simply have the options that the question is, for example, are you satisfied at your job? And the recommended answers are very, for the most part, half and half, not very much, and no, I'm not satisfied. So these are the answers, okay? Instead of having this data as text, or yes, I am satisfied, or mostly, or rarely, the analysts transforms the data into numbers. So I am satisfied becomes 5. Almost all of the time becomes 4. I'm not sure becomes 3, and so on. So this is data transformation. Data cleaning is completely different. It's basically removing stuff that doesn't belong. So why do we have to do it, and what's the benefits of doing data cleaning? Well, basically you're going to get a better outcome. The outcome and the conclusions are just as good as the data set. You get a bad data set, you're going to have shoddy conclusions and not so much substantiated results. It's going to increase your efficiency or accuracy, especially if what you're doing is a quality project. If you're talking about data from a medical facility and you're going to use it to improve the quality of service, it will help to preserve your reputation. So if you are a firm, for example, like Press Ganey, we use this, it's an international firm that actually measures key index performance, key performance index data that actually measures the outcome and the performance of departments and factories and so on, and checks for patient satisfaction. When you use accurate data sets, then you have a reputation to have good, accurate, reliable results. For example, last time I was talking to you, one of the sites I mentioned was the Cochrane collaboration. This is a site that actually has to do with a lot of very high quality evidence analysis. And they get this reputation because they scrutinize the data in a very, very good way. You get the benefit of having an error-free conclusion. It will conform to your model or to your concept that you're trying to prove or disprove, depends on what your question is. And obviously, it will remove the oversampling. If you're supposed to only have 200 subjects in your study and you've collected 300, you don't need that extra 100 to increase your error. Even though it will give you extra information, that's not always a good thing. So you can see the benefits to data cleaning. Now, of course, just like you have benefits, there are challenges to data cleaning. So it is extremely, extremely time confusing. Remember, the analysis and the calculation is done by computers and it's done by software. So all you have to do once you enter your data set and you've cleaned it is just to make sure that you choose the right statistical analysis, as you will be learning in the next couple of hours, and to make sure that you know, the confidence intervals are okay and the range is okay and the test that you're performing is the correct one. But 80% of your time, or of the analyst time, let's say, is actually cleaning up your data set, okay, removing the errors, so that once you start the program, the program is not going to give you any problems, or it's not going to give you any error messages telling you that certain parts of the data cannot be computed, or there's a division by 0, or whatever. Of course, the scales that you need to imply may be different. So you can basically clean the data manually or by hand if you're talking about a survey of, let's say, 200 people. You can go through that number. But if you are working on an analysis that involves hundreds of thousands of subjects, like you see in the cardiac trials, if you are dealing with a study that deals with, let's say, 12,000 people or 30,000 people, you're not going to be able to do this manually. It's just going to take too long. So you need to scale up the technique. You need to employ programs that actually systemically look for errors. It's just like when you write a letter and you perform a spell check. You're not going to read every single word in the novel or in the letter that you've written. You have the program go through it and make sure that every word is spelled correctly, every grammar rule is obeyed, and it will flag anything that doesn't look right. The other thing is privacy and security. You are dealing with proprietary information. You are dealing with information that does not belong to you. It belongs to the patients. It belongs to the hospital. And in some cases, it belongs to a company, the ones that are paying for the study. So you cannot get the data set shared with somebody who's not cleared or he's not part of the study. So you must maintain the security and the privacy of your data. And that could be a challenge if you are dealing with unreliable sources. Plus, you can have, we already talked about having it done automatically or manually. Now, data quality problems are as follows. So they are two main types. It depends if you're getting your data from a single source or if you're getting them from multiple sources. So are you just running the data or are you running the study in a single center where you can actually control what's going on, or you're having it in multi-center fashion, or it could be not even in multi-centered, but in multiple countries. So you would have a hospital in the US, another hospital in the UK, another hospital in China. And because of that, you're going to get a lot of dirty data. So you need to clean this up. Now, if you have a single place, the problems arising for data cleaning come at two different levels: the schematic level and the single instance level, or the observer level, if you like. So the schematic level, this is a problem in design. So it just means that you didn't design the study properly. When you put your data set, you can see from surveys that you filled in the past, for example, if they ask for your age and by accident you press enter and you don't put your age, it will give you back a message that says this field is required. So this is something that was placed in the design to prevent you from circumventing that field. So you need to have such things if you are going to ensure that your data set is complete. Okay, so you need to preserve uniqueness. So you should not have two patients with the same identification number. You should not have incomplete answers. So if you're doing a survey, for example, and somebody doesn't put their age or doesn't put their sex or doesn't put their occupation, that's going to create a problem for you later on when you come to do the analysis. Are you going to include those people that had incomplete entries or not? Okay, so this is the idea of identifying whether or not you have a good data set or not. On the interviewer level or on the personal level, the person who actually enters the data or collects the data, you can have misspelling because they're not good in English or they're not good in typing. If they're taking the data on a laptop or on a data pad, okay? If the person themselves are filling in your data, you might have a problem reading the handwriting. And we've seen this always. For example, you were asked to fill in your emails for this course so that they can mail you, or you were asked to input your Saudi registration number so that they can actually give you the continued medical education hours. Now, if you don't do that, if we get someone with an empty email or a wrong email, they're not going to get the CMEs. So this is exactly what is being done. So things that are misspelled will be counted twice as two different entities. Duplication because you have a hyphen instead of a stroke, for example, or because you have a capital letter instead of a small letter might be a cause of bias. You might have contradictory values. Okay, so even though it will say, you know, the patient has a husband, you find out that they are pediatric age, for example. Age 8, for example. Okay, so this is kind of a contradiction. Or you might have an outlier, and we're going to talk about those later on. If you have multiple sources, again, you have problems at the schematic level, in which case you have more than one model. Maybe your system in Saudi Arabia is different than the system in China. Maybe the system in Saudi Arabia is different than the system in the US. So here, for example, we call the oversight Sibahi, whereas in the US, they call it the Center for Medicare and Medicaid, the CMMS. Okay, so this is a naming conflict. We have to name things the same thing, okay? And they should have the same jobs. You might even have a structural problem, okay? So if you're running the study in a military hospital, for example, you might have military police, whereas if you're running it in a Ministry of Health hospital, you might have security guards. Now, they don't perform the same function, and therefore, the whole structure might be different, and this could be a source of error. What are you going to do with the data that comes from one place and the data that comes from another place, but both things don't mean the same thing? So this is a source of bias. And again, in the interviewer level, you might have inconsistencies. You might have an overlap. So, for example, in some hospitals, people who handle fire and safety are the same people who handle maintenance. Whereas in other places, you might have a maintenance crew that deals with electricity and water, and another crew that deals with fire. Okay, so interviewing those people might be different if you are including them in your study, for example, and you might have inconsistent entries belonging to the same groups or different groups because you have different structures. So these are the problems you will face. Now, how do you go about cleaning your data? Well, we have a number of steps like before. So the first thing that you're supposed to do is remove any duplication. Okay, if you have somebody that basically is interviewed by one data collector and then is interviewed again by another data collector, they might be given different identification numbers, but the data is kind of the same. So the data might be recorded from a number of sources or counted twice or counted for the same person, and this will introduce error into your data set. So that's your first thing to do. The second thing is to remove any of the scrap data. And the scrap data is kind of data that you really don't need. You've collected, but you've collected just to make sure that the other parts of your data set is accurate. It's either irrelevant data or out of range, or for example, you have the name and the name says 3XY. Doesn't really mean anything, or what's the job and there is no job. So for example, this is an example of a study that we've done. It was a survey, and you can see here that we've done this on SurveyMonkey, and the platform that we did the study on automatically collected the type of device that the subject used to fill our survey. So how many people access the survey through their tablet, through Windows, through their Mac, through their iPhone, or through their Android. And it gives you here how many people use the iPhone, how many people used a Galaxy phone, for example, or an Android phone or tablet, how many people use desktop Windows. So this is data that has been collected. However, it is not something that we were interested in. So this is scrap data. It's just extra stuff that was forced on the data set as something that was basically offered by the platform that we used. We didn't ask for it. This is not part of the survey. So incorporating this data and sending this data to the analyst is just going to create clutter. It's just going to create extra stuff for them to do, which I'm not interested in finding out the different usage. It doesn't mean anything to me that most of the people used Windows. There is irrelevant data, for example, that is part of the study. The same study that we actually did, we were asking people about their knowledge of CPR. And one of the questions was, where did you get your information? Did you get it from a book? Did you get it from TV, from the internet? And one of our choices at the end was anything other than what was listed. And you can see the responses. People actually wrote approximating there is at least a dozen typos in this survey, by the way. What do I do with this data? This is just rubbish. It's irrelevant. Where did you get the information? My brain. Well, obviously. Where did you get it? Vague memory. No place. And somebody didn't understand what we were asking. Somebody said, I'm thinking about it. or you asked me what I thought, not what I know. So all of these are really irrelevant, scrap, rubbish data that is just cluttering up and making my data set look dirty. The idea was that, where did you get your information? I got it from a book. I got it from a lecture. So some people might have wrote, for example, I got it from a video I saw on YouTube, or they could just write YouTube or Instagram or social media. That would have been fine. But we get all kinds of stuff because this is what the subjects entered. So this is an example of irrelevant data that you need to clean up and remove from your data set and not have enter the analysis stage. So after you remove all this scrap, now you need to fix the structural errors. So any typos. So if somebody, wrote a text, you have to fix the typos that they wrote, the misspelled entries. Like we've said, some people might write not applicable as N/A. Some people might write the whole thing. Some people might write NA. Some people might write N-A. So, but they all mean the same thing. We don't want the computer to analyze each one as a separate entity. So these are structural errors that you need to get into the same notification. Okay, so as we said, if you're getting data from two hospitals, in one hospital they might use this form, in another hospital they might use this form. Okay, so it is up to you as the analyst or the person in charge of the investigation to actually go through this and clean it up. You need to filter the unwanted outliers. The word outlier just means that it's an observation that is way out there. So for example, if I was to say that the average marks in the final exam for the residency program was pretty much in the 60s and 70s%, except for one person who got a 98%. This is considered an outlier. So it's a piece of entry or data that is very much outside the range. It's not predicted by statistics. It's not predicted by frequency, okay? It's like saying somebody has a blood pressure of 250 over 150. Now, that could be true. It's unlikely. However, it could be. And of course, putting this in your data is going to screw up your average. If, for example, you said, I want to make an average of the amount of money that everybody has in the room, and everybody has like 10 reals, 50 reals, 100 reals, and there's one guy that has a check for 3 million, this is going to make my average at around 150 million, which is completely inaccurate. So these outliers, you don't necessarily have to remove. You may want to remove when you're doing statistics, but having an outlier sometimes proves your theory. It depends on what your question was. Now, obviously, having an outlier doesn't mean that it's incorrect. It just warrants your attention to actually look into that entry. Was it entered properly? Is it an error? This is like when the nurse comes and checks the order for the physician. Did you actually mean 100 milligrams of morphine, or did you write 10.0 and you didn't, put the point? So this is a second way of checking for outliers. Now, handling missing data especially is going to be the rest of this presentation, okay? Because there is no one way to handle missing data. It's the most frustrating thing. Your data set is incomplete. You need to basically have to make assumptions, and of course, it introduces bias into your calculations. Okay, so it can affect your results, and there are three main methods into dealing with missing data. Your number one method to do this is basically to remove anything that's incomplete. Now, this is known as the per protocol analysis. It means that you only do analysis on those subjects that has finished your protocol, that have finished your study, that have completed all the data set, all the fields that you require to finish this study. So you're only going to count those that have complete data. Now, obviously, if you do that, you can actually alter your results. And I'm going to show you an example of how this can significantly alter your results. I mean, you can actually have a trial that was positive become negative, or negative become positive because you did this in the wrong manner. Okay, so you have to be very careful when it comes to removing data from your set. The second method is to apply the best scenario or the worst scenario outcome. And I'm going to show you an example of how this could be useful or it could be detrimental. The third method, and probably this is the best one to handle, is something called the last observation carried forward. In other words, the last time that we've had, that we know about this subject before we lost him from the study, we're going to assume that that's the last thing that happened to him, and we're going to continue to have that state all the way to the end. Again, I'm going to show you how this works. So after you've done that, after you remove the duplicates, after you've removed the errors, you've fixed the structural problems, you've removed the scraps, you've found a way to handle the missing data, now you need to validate your clean data set. So does it make sense? You need to ask yourself, does what I'm seeing make sense? Does it follow the rules? Do I have a number where the age should be entered? Do I have a text where the name should be entered? Or do I have, inappropriate format? Does the data actually show a pattern? Does it prove the null hypothesis or the working hypothesis? And is there a trend to my data? So I need to go and validate the set. And if for any reason I cannot do that, I need to answer the question, is this due to the quality of my data? Do I have a really bad data set, or is it something else? So this is what I need to do. The criteria for having a good quality data is I have to have a data that's valid. It's the measure or degree to which the data conforms to the rules that I've defined in my design study. Does everybody in my study fulfill the inclusion and exclusion criteria? Do they actually follow the definitions that I've set in my question? So this is the validity. The accuracy, how close is the data to the actual value? Okay, am I seeing something that I'm expecting, or is it a complete surprise? And is there an explanation to this? Is the data set complete? Did I actually fill everything I need to fill? Did I get all the items of data that I need? or is there something that I couldn't get? So it's a measure of how complete my set is. Is it consistent? Do I see the same trend throughout the study? Or do I see, in some cases there is benefit, in some cases there is harm. It's all over the place. I can't really get a trend throughout the study. So this is important. Is it uniform? Is everything being defined in the same way? Are they having the same units? Do I, if I'm, for example, if I'm dealing with blood gas analysis, is everything written down in, is the partial pressure of oxygen or partial pressure of carbon dioxide being reported as millimeters mercury? Or is it being reported as kilopascals? Or is it being reported as atmospheres? They're all acceptable ways, but I have to get them into a uniform way of measure. Just choose one and change everything to that. Okay? Do I have all of that? That's the mark of a good quality data set. Now, this is a couple of examples of how playing around with missing data and your choice of how to handle the missing data can actually change your results. So what we're going to do is we're going to have a hypothetical experiment. So this is hypothetical experiment number 1. Let's say, for the sake of argument, that we have a drug S, and this drug is supposed to reduce the risk of patients having a new stroke once they've had a first one. So the people in this study, they've all had a stroke. And I'm going to give them drug S to prevent them from having a second stroke. Okay? So secretly, I'm going to tell you that drug S doesn't actually work. It has nothing to do with prevention of strokes, but of course, since you're running the experiment, you don't know that. I'm just giving you this information to show you how it's going to change the results. Okay, so the group has decided, there's a group that decided to try drug S in a well-designed RCT. You've designed a well-designed randomized controlled trial to see if there's any benefit to drug S. So what is my question and what is my P-cut, if you remember? Okay, so this is my P-cut. I'm going to choose 200 patients, all who have had CVA in the past. 100 of them are going to receive the intervention. So 100 are going to get drug S for 1 year. The other 100, they're going to get placebo for 1 year. And what I'm checking for is how many will develop a second stroke over the study period, which is 1 year. So this is my question. So now, from the beginning, I'm going to randomize my 200 subjects into people that will receive drug S and people that will get placebo. So I'm going to get 100 into every single group. And they're going to get this therapy or the placebo for 1 year. And the outcome is I want to find out how many people develop stroke. So let's say, for the sake of argument, that 20 people in the drug S group decided, you know, I don't want to take drug S anymore. It's horrible, it's expensive, I don't want it, and they just stopped taking it. So 20 of the 100 that went into the experiment group did not complete the study protocol. So after 1 year, I have 20 people that didn't complete the study. So this is missing data, okay? I don't know if they had completed the study, if they took the drug as it was supposed to be. So they took the drug, let's say, for 6 months. Maybe if they took it for 1 year, they would have been saved a second stroke. The thing is, they never completed the study, so I don't know. 80 people from the 100 that I started with completed the study, and the people who took placebo, they all completed the study. Now, let's say for the sake of argument that the risk of having a stroke if you don't do anything is 20%. So if you've had a first stroke, your risk after 1 year is 20%. So this is the number of stroke that you're going to end up with. So in this group, 20 out of the 100 are going to have a second number of stroke. And here, out of this 100, because remember, drug S has no benefit and no effect, as I told you, they're going to have 20 as well. Now, this is how this is going to change. If I do a per protocol analysis, if I remove these people, the 20 that didn't complete my study, I have 8 people, but now instead of 100, I have 8 people out of 80. So 10% have suffered the outcome in the drug group, whereas 20% have suffered the outcome in the control group. So the control group now looks worse than the experiment. And if I calculate the relative risk reduction, taking drug S has 50% benefit. So by removing the incompletes, I found out that a drug that had no benefit actually came out to have 50% benefit. So you're half as likely to develop a stroke if you use drug S than if you use placebo. So drug S seems like a good idea. Now, if I was to do the analysis the way that it was supposed to be done, okay, the way that we usually do it with intention to treat analysis, I'm going to explain this in a moment, okay? So if I do this and I include the people who have had the strokes, even though they didn't complete the protocol, so a total here of 20 out of 100, I will get no benefit, the true effect. So why is this changing? What is intention to treat analysis? The goal of intention to treat is to prevent bias being introduced by prognostic factors, like what you saw, okay? The deal here is even if I have people that didn't adhere to the protocol, once they are in the study, I should calculate them in the analysis. So if they were randomized, they should be analyzed. And if they're analyzed, they should be analyzed as they were randomized. If they went into the treatment group, they should be counted in the treatment group. The problem is I don't know how to count them, okay? Now, the reason why there was a benefit in a drug that didn't have any benefit was because when I did the per protocol analysis, okay, the non-complier group, the people that didn't complete the study, actually had an outcome of 60%. They had 12 strokes in 20 people. So by removing these from the analysis, I removed the 12 strokes from the people who took the drug from the experiment group. So the experiment group looked less bad. It looked better because I removed all of these strokes from it because those people didn't complete the study. So the drug looked like it had benefit when in fact it didn't. So you have to be very careful to apply the intention to treat analysis when you're handling missing data. So the only time that you can do a per protocol analysis is if the non-complier group has the same prognosis as the complier group. The problem is, when are those two groups identical? And the answer is they're never identical, because you have one group having the therapy, whether the therapy is good or bad, it should either make those people better or make them worse. Now, if you stop taking a good drug, you're going to have a worse outcome. And when I remove a worst outcome from one group, that group looks better. Now, if that drug is causing harm, then if I remove that harm, I'm going to make the group look better. So if it has benefit and I remove it, the group looks worse. If it has harm and I remove it, the group looks better. The only time when this is the same is if the drug absolutely has no benefit whatsoever. And that is very, very rare. So another example to show you the best and worst case scenarios. This is probably easier for you to understand. So let's say we have subjects lost to follow-up, and this happens in studies all the time. Okay, you start with 100 people, and then when you follow them up, by the end you have 80 or 70 people. Okay, so we lose subjects to follow up all the time. People stop coming in, they stop taking medication, they stop checking in, so we don't know what the final outcome is for those people. Now, we don't know if we're studying mortality, for example, we don't know if they died or if they're still alive. Okay, so the question remains is, how much can we lose to follow up? How much missing data can the study tolerate before it invalidates the results? And how can we deal with this missing data? Well, let's say that we have two trials. So trial A, we're dealing with 2,000 subjects. We're testing drug A, okay? And the outcome, let's say we're talking about mortality. So let's say that drug A has 50% benefit. So the group that took drug A, only half of them died when compared to the group that didn't take drug A. Okay? Now, let's assume that we have 3% of each group lost to follow-up. Only 3%. Okay? Since we're testing benefit, we might as well look at the missing data in the worst case scenario, because if I assume that those people that were lost to follow-up all have died and the drug still has benefit, then that's the worst case that it could be. So in other words, if anything happened, it's going to be better than that, so the benefit still stands. Okay, so this is trial A. Trial B is exactly the same, but we're using a different drug. We're using drug B. Same thing, drug B causes only half the deaths. Same thing, we have 3% lost in each group. Now, this is what's going to happen. So this is trial A. So the number of subjects that's receiving the therapy is 1,000. The number of control is 1,000. How many lost to follow-up? 3%. So 30 here, 30 here. What's the number of events? How many people died in the therapy group? Let's say it's 3%. How many people died in the control group? It's twice that, 6%. So now, if I did the best case and the worst case scenario calculation, this is the way it's going to come out. So the best case scenario says the experimental event rate is 3%. 3% died. Best case scenario means that all of the follow-up, the ones that were lost, they were considered to be alive. That's the best case. So only 3% died. The control experiment, we're going to assume the best case scenario. So here, the 3% died as well as the 6% from the control group. So the event rate is going to be 9%. That's the best case. Best case means that everybody survives in therapy, everybody dies in control. So if I calculate the relative risk, 3 divided by 9, I get a 33% relative risk, and the relative risk reduction by giving them the therapy is 66%. which means that if I give the therapy, I'm going to improve the survivability by 66%. That's the best case scenario. Now, what's the worst case scenario? Well, the worst case scenario is that all of the therapy group have died. So the experimental event rate, instead of being 3%, is 6%. And all of the control group have lived. So I only have these who died. The 3% here has actually lived. So if I calculate the relative risk, it's 100, which means that drug A has no benefit whatsoever. So here you can see I went from 66% to 0. Huge. Just simply by deciding how am I going to do with those 3%. Now, if I look at trial B, which looks kind of the same, I have 1,000 people taking therapy, 1,000 people taking control, 3% lost to follow-up here, 3% lost to follow-up here, and now instead of having 3% death, drug B is a little bit more dangerous, but still the number of people dying in the therapy group is half the number dying in the control group. Now if I do the best and worst case scenario, so best case, the follow-up all live, so I have 20% death in the therapy group, and the control, they all die, so instead of 40, I have 43, so 20 divided by 43, I have a relative risk of 46.5, so the relative risk reduction, the benefit that I will get from taking drug B is 53%, similar like the 66% we had in the previous case. Now, what's the worst case scenario? Here, all of the people in the therapy group died, so I have 23%, and none of the control group died, so I have the 40. And so the relative risk is 57, and the relative risk reduction is 42. So see, when I did it in trial A, I went from 66 to 0, whereas here I went from 53 to about 42, a 10% difference. So the third thing I can do, as I said before, is last observation carried forward. So how can you do this? This is the same trial we've just had. This is trial B. Okay, best case scenario, same as before, 53%. And now, if I carry the same last observation forward, means I'm gonna do the same percentage in the follow-up. What was the percentage of death in the people who took the therapy? It was 20%. So I'm gonna assume that 20% of the 30 had death. And here I have 40% of the control, so I'm going to assume that 40% of the loss to follow-up will have death. This is the last observation carried forward. So here I'm going to have 20% out of 30 is 6 patients, so I have 20.6, and the control, 40%, I have 12, so it's 41.2, and if I do this, I'm going to get something in between. So going from the best case to something in between the best case and the worst case, I don't change so much. Now the question is, why did it change so much in trial A? And the answer is the huge difference between the intention to treat and the worst case scenario was huge in trial A and not so much in trial B, because the difference between the loss to follow-up and the event rate. Okay, the idea is when the loss to follow-up is comparable with the number of events. Remember, we had 3% events and 3% loss to follow-up. So if those were considered to be events, you have just doubled your event rate. So the worst case scenario will change the result because your lost data or the missing data is the same magnitude as your outcome. In the second trial, the number of events was large. So the amount of events that you lost was small in comparison to the ones that you do know. And therefore, if you take the number lost or the missing data percentage and you divide it by the number of events, if you're less than 10%, then your missing data is trivial, which means that it will not significantly change the result. Doesn't matter which scenario you use, the best scenario, the worst scenario, the last observation carried forward. If you use any scenario and you're less than 10%, your results are not going to change. If your results changes significantly because your loss to follow-up is similar to the number of events, then you have a problem. Your study has a very bad data set. So if you're trying to show benefit, the best thing you can do is do a worst case scenario, because if that's the worst case, anything else is going to be better. If you're trying to show harm, okay, then you have to use the best case scenario, because if that's the best case and you're still showing that that drug has harm, then anything else is going to be more harm, and therefore you are in the clear. The last observation carried forward is somewhere in the middle. It's kind of a fair way to deal with the data. So handling a missing data, you should have something called an a priori, which means you should have a rule before you start your study. How am I going to deal with the missing data? Before I start, if I'm trying to show benefit, then probably I'm going to go with the worst case scenario. If I'm trying to show harm, I should go with the best case scenario. If I'm trying to just compare different treatments, then I probably should go with something in the middle. So I should have a rule. And of course, the best way to deal with missing data is not to have it in the first place. Try to have a design so that you do not have a missing or incomplete set of data. If you're doing a survey, try to make sure that every field is a required field. The survey will not let you continue until you fill that field in. So with that, I would like to thank you for your attention. This is how you clean up your data, but please be careful that you can actually change your results based on what you have.